Okay. Do only nonpolar molecules have London dispersion forces? All molecules have London dispersion forces. Okay. But they're weak. It's kind of like the sticky stuff on a post-it note that, yeah, that's going to stick to something. But if I use duct tape, it's a lot stronger. So if I take a post-it note and put it on the wall and then put duct tape over it, and you ask, well, what's holding it to the wall? Well, yeah, there's the sticky on the post-it note, but it's really the duct tape that's keeping it from going. So when we talk about things that are ionic, when we talk about things that have uh, dipole-dipole forces, those are stronger than the dispersion forces. Okay, so our basic idea was that the electrons are moving around. At any given moment, they might be on one side of the molecule. And for just an instant, and that word instant is where we get instantaneous dipole, just an instant, it is polar. And then the next instant, it might still be polar, but in a different direction. Okay, so it's constantly changing the direction of its polarity. And during that instant, the positive side attracts the electrons in the neighboring atoms. And then we had just started with this, saying that the size is going to make a difference, okay? Because the more electrons you have, the more zipping around and clustering and whatnot can happen. So we said bromine was going to have stronger dispersion forces than fluorine, carbon tetrachloride more than methane, okay? Shape also makes a difference. So if you had lab on Tuesday, I know Dr. Hughes was trying to look at different shapes of molecules with the evaporation. And I don't know what you guys ended up working with. I know she was trying to find some different things. But if we have pentane, this chain mostly stays folded out. And so we've got this long section that can be attracted to the next molecule over. Okay, so think of a long strip of post-it note attached to something. Whereas this molecule is almost a sphere. And so it just has that tiny little piece that can be attracted to the next molecule. Otherwise, there's a lot of space in between. So the longer the molecule, the less spherical the molecule, we're going to have more attractions. Well, how do we know we have more attractions? The stronger the attractions, the higher the boiling point is going to go because it's going to be harder to get those molecules separated. So our boiling point for neopentane is going to be 9.5. So we would not be able to find this in liquid form at Asher temperatures, even when our heat's off. And then over here, 36.1, that's well above room temperature. So you were probably should have been working with N-pentane in lab. Now that is lower than body temperature. Body temperature is about 37. So if you put a few drops of this N-pentane in your hand, it would evaporate pretty quickly because the heat from your hand would be enough to make that evaporate. Okay, so that was our London dispersion forces. What matters there are the number of electrons. So sometimes you'll see it say mass, but it's really more important is the number of electrons. And then the length of the molecule. All right, so now we're going to get to our new type, hydrogen bonding. All right. Okay, I didn't cover it up. So hydrogen gets this special case because hydrogen's always going to be our problem child. It's not going to behave like the others. Everything that we said about dipoles still applies, but it has this extra strong interaction that it does. We can observe this by looking at compounds that are bonded to very electronegative elements. So what's the most electronegative element? Fluorine. So fluorine, and then the two right next to it, oxygen and nitrogen. If we have hydrogen attached to those, we're going to see this effect. Okay, so we're first going to look at the carbon group. So this bottom black line here has carbon with 4 H's, so CH4, and then underneath carbon is silicon, then germanium, and tin. So going down that column is where we're going across here. And so this is showing us the effect of the London dispersion forces. As we have larger central atoms, we have more electrons, and the boiling point goes up. Okay, so that's the effect of London dispersion forces. Those are nonpolar molecules. Now the others are all polar, so we expect the boiling points to go up a little bit. If we are looking at the halogens, here's hydrogen iodide, hydrogen bromide, and hydrogen chloride. As it gets heavier, it goes up with the exception of hydrogen fluoride, our most electronegative element. So hydrogen fluoride should be a lot lower than the others because it has fewer electrons, but it's way high, okay? Same thing for ammonia. It's a lot higher than the others in its group. Now, it's not quite high enough to be higher than antimony trihydride, but it's pretty close, right? And then water really is a much higher boiling point than all the others in this group. And this is attributed to hydrogen bonding. So the intermolecular, from one molecule to the next, attractions between hydrogen and electronegative atoms is quite strong. And so when we say electronegative, we mean N, O, and F. So those have electronegativities of 3 or higher. Now, chlorine's electronegativity is pretty close to nitrogen, but it's bigger. And so the concentration of the electrons is not quite as much. So we get sort of a pseudo hydrogen bonding in there. Traditionally, we just say NO and F. Okay, so because that interaction is quite strong, the hydrogen bonding occurs with molecules that have NH, OH, and FH bonds. Now, the hydrogen has to be attached to this electronegative atom because it's pulling electrons away from the hydrogen. Hydrogen only had one to begin with, so what's left over hanging out on the other side? Just that exposed proton, right? Just the nucleus. And so that hydrogen is very positive. Now, if I have a carbon-hydrogen bond, they're sharing pretty darn equally. And so I don't really have that exposed proton the way I do on these others. So even if a molecule has, like this one does, it has hydrogens and it has oxygens, I don't see hydrogen bonding in this because these hydrogens don't have that exposed proton. Okay? So the hydrogen has to be attached to the oxygen, the nitrogen, or the fluorine. All right, so sometimes we will draw this with a dotted line between the hydrogen of one molecule and the oxygen, nitrogen, or fluorine of the next molecule. What part of that molecule is it going to be attracted to? Is it going to be attracted to another hydrogen? No, you can see these are attracted to the oxygen, and in particular on that oxygen there are lone pairs. And so that's also going to be really key, is that those lone pairs are a high concentration of negative, the hydrogen is a high concentration of positive. So it's not quite an ionic interaction, but we're leaning in that direction. So the OH bond is very polar. The electrons are not shielding that hydrogen nucleus. That becomes very positive. And the hydrogen is also very lightweight. It only has one proton. Okay, so this doesn't happen with lithium or sodium or whatever. They're heavier. The hydrogen is very lightweight, and so it's easily attracted to other molecules. So that gives us our last one on the list, hydrogen bonding, and the key thing there is looking for OH, NH, and FH. All right, so if we are asked the question for a simple molecule, now if we had the complex one like the one I drew on the board before, there's kind of a lot going on there. But for the basic molecules we were doing VSEPR structures of, if we were being asked what sort of interaction of these four is the most important or the strongest, then we would need to be able to figure out, first of all, what is it made of? Then, what is its shape? Okay. And those would tell us Is it ion-ion or hydrogen bonding? And is it polar or non-polar? So if I look at something like sodium chloride, I know that's ion-ion. How do I know it's ion-ion? Do we know that sodium forms ions and chloride forms ions? Yeah, okay. If there is a metal and a non-metal together, that's ionic bonding. That's why we spent time in chapter 7 talking about the different kinds of bonding. So all I'm looking for to see if it's ionic is it a metal and a non-metal? Okay. And since I don't have metallic bonding on this list, because metallic bonding is kind of all over the place, if a metal shows up, it's probably ionic. Okay. So the first question we ask ourselves is the compound composed of a metal and a non-metal? If the answer is yes, I'm going to go over here to the right-hand side. And I'm going to say if there is a metal and a non-metal, then the interaction is ion-ion. If the answer is no, then I need to know more about the composition and the shape of the molecule. So I'm going to ask myself, are there polar bonds? So I don't really need to know the shape of the molecule if it's all made up of the same kind of atoms. So nitrogen, nitrogen, no polar bonds. Carbon, carbon, no polar bonds. So basically, if it's all the same element, it's probably not polar. The exception is ozone, because ozone is bent in shape and has that lone pair. But other than that, if you see something that is all one element, then it's not polar. So it's going to have London dispersion forces. So nonpolar means the dominant force is London dispersion forces. Those two things go hand in hand. Now I can have molecules, I can have molecules that have polar bonds that are nonpolar if they're opposite one another. So carbon dioxide, remember, if my head's the carbon and then my arms are the oxygens, like the oxygen pulling in this direction and the oxygen pulling in this direction are exactly opposite one another. So it is possible to be nonpolar if there are polar bonds. So then I'm going to ask myself a couple more questions. First of all, I want to know about hydrogen bonding. So here's my composition question. Do I have OH, NH, or FH bonds? That's where you need to pay attention when you have those formulas written out that tell you about the structure, the condensed structural formulas, because they're telling you what atoms are attached to each other. So if I were going to do the condensed formula for this guy, I would write CH3 OCH3. But if I had ethanol, which has the same number of atoms and the same kinds of atoms, has 2 carbons, 6 hydrogens, and an oxygen, I would write CH3 CH2OH. So these two are what we call isomers of one another. This one with that OH written together, that's telling me hydrogen bonding is involved. Okay, so that's why it's important to be able to read those. Okay, so these two are isomers. And this one we would say has hydrogen bond. All right, so if there are OH, NH, or FH bonds, then we got hydrogen bonding going on. If there are not, then we're back to dealing with the shape of the molecule. So this is kind of a long-winded way of saying, is it a polar shape? So do the bond dipoles cancel out due to molecular shape? Well, that's saying if I have the polar bonds like carbon dioxide, are they directly opposite one another? Then that's going to be nonpolar. Okay, so if you know the shape that's a tetrahedron is nonpolar, that's all that question is asking. So if I got a polar shape, is polar. If I got a nonpolar shape, it's probably nonpolar. All right, so if they do cancel out, we got London dispersion forces. If they don't cancel out, then I've got dipole-dipole forces. All right, so those are our various forces there. So let's take a look at this methyl ether that I have on the board. Does this have a metal and a non-metal? Any metals in this? No, no metals. Okay, so we're going to go down to the next question. Are there polar bonds? Basically, this is saying, are there any bonds that are from two different elements? And if there are, there's probably polar bonds. So carbon, oxygen, that's a polar bond. All right, so there are polar bonds in here. So we're going to go over to, are there oxygen, hydrogen, nitrogen, hydrogen, or fluorine, hydrogen bonds? Is there an oxygen-hydrogen bond in this molecule? No. There's both an oxygen and a hydrogen, but the oxygen and the hydrogen are not bonded together. Okay. So now we're down at the question, do the bond dipoles cancel out due to shape? And this is where showing this kind of at an angle here illustrates that this is a bent shape. And we know bent shape with lone pairs on our central atom means that they don't cancel out, that this is a polar molecule. Okay, so the strongest or dominant force for this one would be dipole-dipole interactions. Okay. All right, so let's try a few more. Chlorine gas, what do you think? Who thinks that's ion-ion? Who thinks it's hydrogen bonding? Who thinks it's polar? Who thinks it is London dispersion? It's London dispersion. Okay, all the same atoms. One other thing I want you to add to the list for that first group is that if it is only carbon and hydrogen, if that's all that's there, we call those hydrocarbons. This is always non-polar. The bonds are slightly polar, but the symmetry will always cancel it out. Okay, so you don't have to worry about if it's like a really complex shaped molecule that you're like, I don't know what the shape of that is. If it's only carbon and hydrogen, it's considered non-polar. Okay, NH3. I'll give you a second to look through your list. Now, the point where you get to the shape on the list, you might have to draw a dot structure to see if there are lone pairs. Does anybody think this one is metallic, or sorry, not metallic, ionic, have ion-ion interactions? What about hydrogen bonding? A couple of takers there. What about dipole-dipole? A couple of takers there. What about London dispersion being most dominant? Okay. It does, in fact, have London dispersion forces, and it is a polar molecule, but because it has nitrogen-hydrogen bonds, that was one of our three, that's going to be hydrogen bonding. Okay? Ki. Few seconds to look at your list. All right, how many think this is ionic? Ion-ion interactions. Lots of takers on that one. Okay, so if you didn't go for that right away, remember that our metals are everything in the middle. We call those transition metals. And those two groups over there, those are all metals. And then this stuff in the lower left-hand corner in the P block, those are also metals. And it's only the ones in the upper right-hand corner that are non-metals. Okay, so yes, potassium is a metal, iodine is a non-metal. All right, this one's kind of tricky. You might have to draw out the molecule, CH3F. All right. Anyone think this one is ion-ion? Good. Non-polar London dispersion forces? Good. Hydrogen bonding. Okay, that's why this one is tricky. Very good, you didn't fall for it. The hydrogen is not attached to the fluorine, so this is not hydrogen bonding. But is it a dipole? Absolutely. This is a polar molecule. So even though this shape would be tetrahedral, because this is a different atom, so remember that was our one qualification for the shapes, is that They are nonpolar if the outside atoms are all the same. But if we have different outside atoms, this one's a different outside atom, then this can't balance with the hydrogens that are around it. And so that one's going to become polar. All right. So we mentioned boiling point. There are several properties of molecules that can be affected, by the interparticle forces. So basically, they all come down to the idea that the molecules are going to be clinging on to each other, and they're going to be harder to separate, and they're going to be harder to move around one another. One of these is solubility. Okay, so we have to remember that like dissolves like, which means that if we have the same interparticle forces, they're going to dissolve one another. So we said ammonia had hydrogen bonding. Water also has hydrogen bonding. We can mix those together very, very easily. Okay, so if you ever use ammonium hydroxide in lab, that's all kinds of hydrogen bonding going on there. If I have oil and water, oil is basically all hydrocarbons. There's a little bit of oxygen in there, but it's mostly hydrocarbons. Whereas the water has that very polar and also hydrogen bonding. Those don't mix very well. Okay. Now, because most things that have hydrogen bonding are also polar, most things with hydrogen bonding are going to dissolve polar things. So water dissolves a lot of stuff because it's polar, so it can dissolve all of the polar things. Ionic things, it's going to depend on how strong that interaction is. So if I have charges of +1 and -1, those are pretty soluble in water. As I start to increase the charges, or as the molecules get smaller, then as the ions get smaller, then it's harder to dissolve in water. All right, another one is surface tension and capillarity. So on Monday, I'll have a demonstration of this one. But the idea of surface tension, if you've ever seen like little bugs that can float on the top of water, or if you've seen like a leaf floating down a river, why is it floating and not sinking in? It has to do with surface tension. So we'll talk about that one more on Monday. Boiling point and melting point. So these go hand in hand. Usually as the boiling point is higher, so is the melting point. And if we're talking about ionic compounds, we don't really boil ionic compounds because they're solids at room temperature. So we talk more about their melting point. So if we can compare the melting point of ionic compounds like sodium chloride to the melting point of wax, wax has a very low melting point. You probably don't even need to get it above the boiling point of water. You just put it in hot water and wax will start to melt. But for sodium chloride, even if I put it in in a dish on a Bunsen burner and have a flame going at it, I'm not going to melt it. So very different melting points. Vapor pressure. So vapor pressure kind of runs in the opposite direction of all of these others. So these first three, the stronger the force, the higher this is. Well, I guess solubility isn't higher. It's just, is it similar? But okay, surface tension and boiling point and melting point. The stronger the forces, the higher the boiling point. Stronger the forces, higher the melting point. Stronger the forces, the higher the surface tension. Vapor pressure goes in the opposite direction. So if I have something that has only London dispersion forces, like the liquids you were working with in lab, you could probably smell them while you were in lab because they turn into vapor very readily. Okay, so weaker forces make higher vapor pressure. Means it turns into vapor or turns into a gas much more easily. And then we have viscosity. So viscosity is the resistance to flow. So this applies to our fluids, not our solids so much. So we kind of use water as a reference, though water has a pretty high viscosity due to its hydrogen bonding. But if I take stuff that has even more hydrogen bonding and put it in water, like sugar has all kinds of hydrogen bonding. That makes it very, very thick. So think of honey, think of syrup that you might put on pancakes. You've probably heard that molasses is very slow. We increase that resistance to flow by increasing the attraction of the molecules. Okay, so all of these are going to be affected by the strength of the properties. All right, so I mentioned this a little bit. I'll just quickly go through solubility. Polar solvents like water are going to be attracted to polar solutes. That's our like dissolve likes. Nonpolar will go with nonpolar. Now you might ask yourself, well, if they're not really attracted to one another, why would they mix together? But it has to do with those dispersion forces. They have those weak attractions, and also because, randomness, just as you're mixing things together, it's not going to suddenly organize itself out and say, no, I was over here and they were over there. Once you mix two different oils together, they're mixed together. Okay. So between randomness and dispersion forces, those mix. And then we said that polar, especially things that have the really strongly polar, like the hydrogen bonding is a strongly polar interaction. That's going to help dissolve our ions, especially if the ions have weak lattice energy. And the weak lattice energy, we said, was the charge was going to be low, +1, -1, and especially if they are large ions. So our polyatomic ions tend to be pretty soluble. Acetate is soluble, nitrate is soluble, sulfate pretty soluble. And then the last thing, remember I said, is that molecules that have hydrogen bonding tend to be polar. So if one is hydrogen bonding and one is polar, most likely they're going to dissolve one another. All right, so here's a little more on viscosity, which I can call sometimes non-pourability by definition. Okay, so if it's more viscous, it's going to pour slowly. So we have, this is probably something like corn syrup, very difficult to flow. Or you might think of like silly putty, where, it doesn't really keep its shape. If you turn it into like a cube, it's going to go, but it's going to do that slowly. Okay, so this is viscous. This is not viscous, so this would be in oil. So as we have higher intermolecular attractions, especially hydrogen bonding becomes important with these, then we tend to have more viscosity. Now, if I'm comparing different oils, what's going to be more viscous? Something with a short chain of carbons, like 6 carbons, or something with a long chain of carbons, like 20 carbons, which will be more viscous. Which has more interactions, stronger interactions, the shorter or the longer? The longer, right? So the longer something is, the more places it can be attracting to something else. It's like using a longer piece of tape to stick something to the wall, okay? So if I'm being asked about something that has the same intermolecular forces, then I'm going to go to how long is it or how many electrons does it have, okay? So if I'm comparing oils, the longer one. All right, so as I said, we'll look at surface tension in more detail on Monday and kind of wrap up this portion. And then we'll start looking at heating and cooling curves.